closer to over there. So this is more along the lines of what you are used to seeing for these arrangements on the periodic table. So again, remember here that the S's can hold a maximum of 2, the P's can hold a maximum of 6, the D's can hold a maximum of 10, and the F's can hold a maximum of 14. So this is called electron notation. Now, if you follow an expected order of things, then you would expect that the lowest amount of energy here would be the 1s. First energy level, 1 subshell, lowest, closest to the nucleus. Then at the second energy level, there are 2 subshells, the S and the P, and you would expect it to go S and then P. And then at the third energy level, there are 3 subshells, S, P, and then D. See how this is growing? At the fourth energy level, there is S, P, D, and F. At the fifth energy level, past F, you can go G, H, I, but we'll never, ever, ever get there because there are no elements with any electrons in those. So you would expect it to simply go in that order, and that would be great. Except in reality, remember, as you get further and further out from the nucleus, these shells get closer and closer together. So remember, we talked about this before. If this is your nucleus with your protons, this might be electron level 1, and this might be electron level 2. So this is 1 and 2, but remember, they are not equally spaced. So 3 gets a little closer, and 4 gets a little closer still. And by the time you get out to these levels that are 4, 5, 6 out there, they are so close to each other, they begin to overlap. Watch what happens when you take the shells and put them into subshells. So here is S, the 1s, because again, the first energy level only has the 1 subshell, so nothing happens there. But here is the second energy level. But remember that the second energy level has 2 subshells, and notice how they split. And they split a little high for the P and a little low for the S, so they split. Well, that's fine. They're still pretty far apart. Well, what about the third energy level? Well, by the time you get to the third energy level, we're a little bit closer, and they split a little bit closer to each other as well. So you've got 3s, 3p, and 3d. But by the time you get to the fourth energy level that's there, now we've got a problem. Now you can see that the fourth energy level, the S subshell for the 4 that's here, splits so that it's actually lower than the corresponding 3D from the previous energy level. And if this goes on and on and on, it gets really complicated. Holy cats, look at how complicated that gets as far as all of the different overlapping is concerned, because those electron shells get closer and closer and closer together. So what are we going to do? How are we going to keep track of this? Well, thankfully, we really don't have to do a whole lot of work if we remember a couple of tricks. A couple of different ways that I can present this to you. I'm not sure which one you're going to be a fan of, but you could start here. So for example, you could start with the 1s's that are down here by themselves, right? First energy level, only 1 subshell. Then you go to the second one, and you notice that we have 2s and 2p. We don't have a 2d or a 2f because we're only at the second energy level, so we only have 2 subshells. The third energy level, however, has 3 subshells, S, P, and D. And the fourth energy level has 4 subshells, S, P, D, and F, and so forth and so on. Then why don't we see any G's, H's, or I's on the periodic table? Because they don't fill in a normal way, they fill in a diagonal way. So if you started here, they would fill with 1s, and then it would be 2s, and then diagonally 2s and 2p, and then 3p and 4s, and then 3d, 4p, and 5s, and then 4d, 5p, and 5s, and 4f, and so forth and so on. So if you were to draw this all out, and then draw these diagonal arrows here, you could figure out the order of their filling. Now, I think that's personally a long way to go for this, but it is one method. I think the easier method is to just recognize that because of the overlap that is present, the first D that you are going to experience, the first D that is here, is actually, because of the overlap, going to end up in between here. Sorry. Whoopsie. The first D that is here is going to end up in between the 4s and the 4p. Now again, you're not going to have to memorize this picture, but just know that the first D that you experience is the 3D because that's the first D that you experience here, right? So consequently, the first 3 Ds that you experience are here, but you'll notice that they're actually in the 4th row. So here is row 1, here is row 2, here is row 3, and here is row 4. So you'll notice that the 3 Ds are actually in the 4th row. What do you notice about the 4 Ds? Well, they're actually in the 5th row. What do you notice about the 5 Ds? They're in the 6th row. What do you notice about the 6th D? They're in the 7th row. So if you just remember that the Ds are one less than the row that they're supposed to be in, you're probably going to be in pretty good shape. Or just remember that the first Ds that you encounter are the 3 Ds, and because of that, then you can just remember that really you start here with 3, 4, 5, and 6D, even though they are in rows 4, 5, 6, and 7, respectively. Similarly, the F subshells are going to end up being 2 less than the rows that they are in. So check this out. We're in row 1, 2, 3, 4, 5, 6, and 7, but you'll notice the first Fs that we experience are the 4 Fs, but they are in the 6th row, so the Fs are always 2 less than they should be. So these here are your 5 Fs, but they are in the 7th row. 7 minus 2 is your 5. That is there. So what you really need to remember here is just the order of things. You start with the different blocks. The blocks are S, P, D, and F. The rows are just the rows. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. But the D's are 1 less than they should be, and the F's are 2 less than they should be. So consequently, you will often see things like this, where again, the S's are normal, the P's are normal, the D's are 1 less, and the F's are 2 less. So back to this that we have seen now, what we've got here is we've got, again, less energy and more energy. Our very first subshell here, the ones that are closest to the nucleus, the ones that are hardest to remove, that's those guys. And that's going to be the 1s, and there are 2 of them. So we put a little superscript there to indicate that there are 2 of them. And now our next ones are going to be these 8 that are here. And those 8 are going to be broken into this subshell grouping here. And that's going to be 2s2, and then the 6 are in the 2p, so that's 2p and then 6 that's there. And then next past that is going to be our outer shell, which is only going to have 7 electrons in it. And those 7 electrons are in the 3rd energy level. So your next ones are going to be 3s2 and then 3p5 that are there. And if you follow this all the way through, you can get quite a lot of these different things, and they all begin to do the same thing over and over and over and over again. You're just building one more electron on top of that. So let's find that chlorine example that we just did here. So erase all of this here. Here's the chlorine example that we just did. Here he is here at 17. So all you have to do these guys is start with your first energy level, which is this guy here. So that's 1s2. Then your next electrons are these guys over here, numbers 3 and 4. They are in the 2nd row, S subgroup, and there are 2 of them. And so consequently, those guys are 2s2. And now your next ones that you encounter are these guys here. They are at the 2nd row in the P block, right? and there are 6 of them, 1, 2, 3, 4, 5, 6. So that's going to be 2p6 that's there. Again, we're trying to get up to chlorine here. Your next ones that you're going to encounter are numbers 11 and 12 over here. They are in the 3rd row. They are in the S subshell, and there are 2 of them. So that's 3s2, like so. And then finally, here we are. We're going to get all the way over to here. They are in the 3rd row. They are in the P subblock, but there are only 1, 2, 3, 4, 5 of them. So that's going to be 3p5. That is there. So this is the notation for chlorine. 1s2, 2s2, 2p6, 3s2, 3p5, which again makes sense and is justified if we check out what is going on in its photoelectron spectroscopy arrangement here. We've got 1s2, 2s2, 2p6, 3s2.